in something or other. So the way we are going to do recap of the semester is, we'll start with Murray. Murray is like, oh no. The way we are going to do it, I want you all to participate in this, okay? So we will go around and everyone needs to tell me one equation. We know what Murray is going to tell us. Okay, Murray, you're not allowed to say the ideal gas equation this time. It has to be something else. One equation that you think was very useful from this course that you would like to remember. And of course, at some point, the equations will start repeating. And if we can't really do anything except repeating, then that's okay. We will start repeating. But I would like to, I think there are 20 equations here that we have covered. So let's try to cover that. One equation and one concept. Okay. And we will go through this and then we will come back and look at some of the tricky ones and go through this. Okay. I don't want to go at the speed of light from lecture 1 to lecture 23. That's not going to help anyone. Okay. So let's go with this. Okay. So we will start with Murray. Let's hold on. TDS, or you're almost there. The signs are, you got, I see what you're getting at, but so you might want to write this down in your cheat sheet, okay? No, these things are confusing. Minus SDT plus VDP plus mu dn, right? How to remember this equation? It's really the slope of G with respect to temperature, which is minus S, right? If you had plus S, it won't work. How to remember? Anytime you have to write down such an equation, first thing you should think about is what were the natural variables, right? So for G, the natural variable is NPT. You can already write down, it's going to be dt, dp, dn, right? And then you write down the coefficients. And concept? If you do something slowly, if you do slowly enough, it will be reversible. Slowly enough is the same as reversible. If you do something too fast, it's probably not going to be reversible. Not all slow processes are reversible, but so I will put an approximate sign here, right? Not all quasi-static processes are reversible. But and this is important that you brought this up. So it's good to be careful with these terms. So quasi-static is the same as slow, and then there is reversible. Often we use these two interchangeably, and that's okay. Normally I will just use reversible. Okay, thanks, Murray. Let's go to Swadeep.
My equation was that only.
You have to go different now.
I was that.
I'm sorry, I will go different now. That's the deal, right? You have to cover different ones.
Let's skip the equation.
No, we are not skipping equation. Come on. Okay, I'm gonna come back to you. Venkat. Think of an equation. Which one? Mu is equal to mu naught plus RT ln P. So one bad effect of going in this manner is that we will be doing equations in a non-chronological manner, right? And that's a trade-off. Mu is equal to mu naught plus RT ln P. Can you tell me what is the concept here? Let's just do it this way.
So the concept here is that basically when you have everyone has a function of pressure, it goes as a logarithm of the pressure.
For what system?
For an ideal gas.
For how many components?
One component.
Ideal gas, one component, right? How did we derive this? This actually comes from Murray's equation, from dg is equal to minus sdt plus vdp plus mu dn, right? If you take a one component system, mu dn becomes 0, right? So you can write down dg is equal to, and you should, let me make a note here. This is again good practice for the type of things you will do in exam. Derive this after closing your notes. Try to derive this, okay, for an ideal gas if you can do that. How would we generalize this for a two component system? Venkat. Then PA, partial pressure, for ideal two component, okay? Yeah, mu A is equal to mu naught A plus RT ln PA. And if it's a generic system with any number of components, we throw in fugacity, right? Then we say mu A is equal to mu naught A plus RT ln FA. You might say, well, what is this fugacity? Why should this equation hold true? Fugacity is defined this way, so, and you measure mu, you subtract mu naught and you divide by RT and you exponentiate it. What you get is fugacity. This is the definition of fugacity. It will be equal to partial pressure for an ideal system. It will be higher than partial, it will be lower than pressure, right? So fugacity is non-ideal, it captures non-ideal behavior. Okay, Ben? Oh,
So
yes.
when we have the multiple components and we want to write like the total chemical potential,
Uh-huh.
right?
What do you mean by total chemical potential?
Because I remember in class we like wrote them together. And then it was
Chemical
like,
potential is always for a species, right? It's never
So-
total.
why did we?
Chemical potential is always for one chemical, one species.
Okay, so you can only write.
Yeah.
like that.
Yeah. And you might be able to consider, you might be able to ignore that a chemical reaction is happening. You could define some funky species, which is combination of everything. But generally, chemical potential is one species.
Is it because it's an intensive quantity?
It's an intensive quantity. Yeah, exactly.
Okay, because alright. So as I said, when we did the delta G of the reaction, we did mu B
Mu B,
minus
mu B.
A.
Yeah, but it
So
was
then we
B.
combined those.
Yeah. But it was always either talking about A or talking about B. It's never mu. If it was only mu, then it was me being sloppy and not writing the subscript.
Okay.
Okay, go ahead.
So we had two separate things, like the air phase and the fluid phase. Can we call that phase a component and dividend?
No. You can, but it's gonna make. Why do you want to do that?
Wait, they have the same thing, but what does it have these components?
Yeah, you could do that, but I wouldn't. The leaf component is complicated enough. Okay, Ben.
Equation
Uh-huh.
that gives you
Tell me the equation. Oh, come on. Oh, come on. Gibbs Duhem. Anyone remembers?
del T of.
You still have to tell me another equation. So tell me.
I was going to tell that.
No.
That's why.
No. Sorry.
Seriously.
No. Yeah.
Like how it connects free energy with enthalpy. I really like that. Like del G and del H connection.
Well, we will come back to you. So that says Ni do mu I is equal to minus S dt plus V dt, right? Why is this equation important? Man. This is a good answer. It's a complicated one. You look at it, it's like, why do I even care about it? The best way to think about it is at constant temperature and pressure, what would happen to Ni d mu I? This is telling you at constant temperature and pressure, summation Ni d mu I is equal to 0. So it tells you at constant temperature and pressure, you cannot go around changing every single chemical potential independently. They are constrained, they are tied to each other, right? And this is what led to the Gibbs-Phase rule later. This is the origin of Gibbs-Phase rule. We would not have had Gibbs-Phase rule without something like this, right? In the Gibbs-Phase rule problem, most of you derived, there was a spectrum of derivations, only 2 or 3 of you actually did the full derivation. That's okay. Like Callan does it, so you could have just copied from it if you wanted. But that's where it really comes from. This is the constraint that exists, right? So it tells you all chemical potentials cannot be varied independently. Okay, and that's important. Now, okay, now let's go to Subhadeep.
Yeah.
Okay? You have any more equations that you're going to be like?
Was stolen, but I'm still remaining one. Del G del Ni equals to mu I. So we can like
Mu I
del G del Ni.
partial G by partial Ni, holding what constant?
Temperature, pressure,
And
and other fixed composition that's I not.
N1, N2, and any Nj not equal to I. This is the definition of chemical potential, right?
Here
So,
we can directly measure the.
Yeah.
This one is incredible.
good. So this is key, right? This is the first time we define chemical potential. Now you disturb my symmetry. Let's go to yeah. You tell me, Jonathan.
I would go with just delta S. for the-
No. I'm gonna change the rules of the game a little bit. Since we did mu I is equal to partial G by partial Ni, I want you to tell me other definitions of mu I. Let's talk about chemical potential. Let's get it out of our system, okay?
Okay. It's,
How? No, I will help you. Can you tell me how to define mu I from Helmholtz free energy? No, you're done. It's again this, but what is being held constant? Volume. Yeah, you're absolutely correct. So volume, temperature, and the same N1, N2, Nj not equal to I, right? Why can we write this equation? Anyone who wants to tell me, that will be their equation. Just raise your hand. Yeah, go ahead.
Almost as the natural variables are.
Exactly. So what are the natural variables for A? N, V, T. Now, Jocks, tell me the fundamental equation for A. It's going to be something multiplied by dn, something multiplied by dv, something multiplied by dt, right?
V minus SDT plus median.
What? It's mu dn, that even I remember.
V plus PDV minus SDT.
Is that correct? Minus pdv. In general, pressure tends to be negative of energy, right? Think about it. It goes down to force even. You can think about it. Pressure is always negative of energy. So, and going back to what Anjali said earlier, when I'm writing this, what I really mean is this is summation mu I dni minus pdv minus sdt for a multi-component system. Okay, so this shows us that the chemical potential for any species I can be derived and in the following manner, right? But the only thing is that now you have to hold the volume and temperature constant as opposed to Gibbs, where you had to hold the pressure and temperature constant, right? So chemical potential can be defined from any thermodynamic potential. It's always a partial derivative with respect to number. The thing is what else is kept constant that matters, right? And this later lent G a special status, right? You all did in your homework. Well, you are telling me equation, so okay. Steven?
Ln K equals mu A naught minus u v naught over RT.
Is this correct? This is for the reaction A going to B. Okay, you pick the simplest reaction, that's fine. So in other words, how would you generalize this?
It's relating, since K is the reaction.
Yeah.
It's relating partial pressures.
Yeah, so for this reaction, this would be ln of PB by PA is equal to ln of K, right? At equilibrium. At equilibrium, K is the value of Q at equilibrium, right? So if you know, so what this is telling you that if you went and calculated the reference chemical potential of the species in a chemical reaction, different species, you can go and tell something about what will happen, how much of the different reactants and products will you have at equilibrium, right? It won't tell you how much amount, especially when you go to more complicated reactions like A plus 2B going to C plus 3D. It will tell you something about PC, P3D cube divided by PA. Sorry, why did I write P3D? PC PD cube by PA PB square, right? It will tell you what is the value of this thing at equilibrium. That does not mean it tells you the exact value of the partial pressure, right? Because many possible things can do that. So it gives you a sense of what's there going, what is it going to be. And this can be calculated by knowing the chemical potentials. So chemical potentials are very useful. Okay, Anjali? So you're saying integral around a closed loop of ds is greater than equal to delta q by t. And clearly, Jock has been stalking me on Twitter and seeing my arguments with.
They're very entertaining.
I stopped at some point. I basically said, like, why don't you come to Maryland and spend a semester with us? But I thought it would look like, I don't know, mansplaining or something. Sorry, I'm sorry, I didn't want to do that. But I mean, it really makes the case that people don't even. I love StatMech. You know, sometimes I come across as like I don't like. No, I love StatMech. StatMech pays my mortgage. You know, I really like StatMech. But you don't even realize what you're missing if you don't do thermo. Like you just get obsessed with S is equal to K log W and you move on with it. No, and then yeah. Anyway, okay. So Anjali is saying that if you have a process happening in some space, let's say PV space, right? And you started at this point and you went around, you did ooh, and you came back over here, right? You did a closed cycle. And in this closed cycle, you pumped some heat into the system, right? and you came back to the same point, and maybe you pumped some heat, maybe you gave some heat, whatever, something happened, right? And this process was maybe fast or slow, right? It was maybe reversible, it was maybe irreversible, right? In the general case, if you put in delta Q amount of heat into the system, the change in entropy along the closed cycle is going to be more than equal to delta Q by T, right? If the process was carried at a temperature T. So what happens in a reversible process? The equality holds, right? So then delta ds is equal to delta Q reversible by T. What happens in a reversible adiabatic process? It's zero. What's an example of a reversible adiabatic process? You would like to think it's the universe, but we don't know. No one will know, ever. That's sad. Okay, thanks, Anjali. Yeah.
Remember like when we had that like very long day about how like the dudes only for DGN.
Say again?
You like swore up and down that like we couldn't write DADN holding like volume constant.
Yeah.
Like, oh, it's like, can you explain that? Because now when we wrote it, now it's fine. But you were like the only one that matters is like when pressure temperature is held constant.
Yeah. So it's the thing here is, okay, so let's revisit that. I did swear up and down because it is very true. So dg is equal to vdp minus sdt plus mu dn, right? And this led us to g. We were able to derive from this that g is equal to summation mu I ni, right? dA is equal to minus pdv minus sdt plus mu dn. As you showed in the homework, from this you cannot derive A is equal to summation mu I ni. That's all I meant.
Okay, because we're at constant temperature.
We are at constant temperature and pressure, right? If you're constant temperature and pressure, this term will remain, right? That's the problem. Minus pdv will remain. Volume is changing. That's where it comes from. So it is really minus pdv plus something else, right? That's where it comes from. So this happened because we defined the partial molars in that way, right? That's where it happened. Okay. Because here. Perfect. That's an equation. I can see you are all slightly biased towards middle of the semester for some reason. So maybe you found the later semester easy and initial semester you have already ignored as a bad nightmare or something like that. But this W equation is super important, right? I haven't made the exam, so I don't know, but it's quite possible that you have to calculate the work done, right? And you did trip on this in the first midterm, where a lot of you became very unhappy. Remember, there was that process of expanding into vacuum. There was no external pressure. So if you have no external pressure, the work being done on this system is zero, right? And it's important to remember here that this is external pressure, right? So you can calculate the work being done on a system for any arbitrary external pressure if you know what is the external pressure. But this is now path dependent, right? The work done on a system is going to depend on how you applied the pressure, what was the process that actually happened. If you carry out the process reversibly, what does that mean? What does a reversible process mean? Reversible means you are at equilibrium at every step of the process. How many types of equilibrium do we have? We have mechanical equilibrium, we have thermal equilibrium, we have chemical equilibrium. You might be abstract about it, you might think of information equilibrium, right? In this class, we don't have information equilibrium. I am blabbering at you, you know. In a good PhD, there is an information equilibrium. I learn from my students as much as they learn from me. That's the hope of a PhD. In the course, in the classroom, there is no information equilibrium. It's one-dimensional. So, but if there is equilibrium, then pressure, external pressure should be equal to the internal pressure of the system, right? It should be. So this is true in general. And we can write this as minus P system multiplied by dV at equilibrium, right? So what I'm doing today is once I get some equation from you, I'm also launching off to cover some concepts, right? so I can cover everything. How do we make use of this? Why is the bottom equation better than the top equation? You want to answer first, Dosia? Okay, that's fine. Anyone else?
For some system, we could idealize it and write as the ideal gas equation.
Exactly, but that's an equation of state. Even if it's not an ideal system, we could use an equation of state. That is the point, right?
Yeah.
So that brings me to the concept of an equation of state, right? This equation is not an equation of state, right? dg is equal to this thing. What is this known as? What is the name of these two equations? Fundamental equations, right? They contain all information. However, you can have different equations of state. And remember, early on we showed that fundamental equation implies three different equation of state, right? If you have all three equation of state, then you can go down and write, the fundamental equation. If you're missing an equation of state, you won't be able to write the fundamental equation, right? You will have some unknown coefficient. So an example, what are equation of states? Equation of states have things like, look like PV is equal to nRT. That's the ideal behavior. The next one is P is equal to nRT by V minus NB minus A n square by V square, which is van der Waals equation of state, right? And there could be more equation of state. So if the system is at equilibrium and we want to use the equation Dosia said, which is minus integral of P external dV, and if I haven't given you the external pressure, you're stuck, you cannot calculate the work done. But now if I told you the process is being carried out reversibly, you can use an equation of state, right? If you have no other information, well, then you should use the equation ideal gas law, right? If you use the ideal gas law, so the W for reversible process in ideal gas will look something like W is equal to minus P system dV. That is true for any equation of state, but now you are going to assume the ideal gas law, right? So now this is going to become minus nRT by V dV. Suddenly you have something you can deal with, right? If the process is isothermal, for example, if isothermal, it doesn't have to be isothermal, but if it was isothermal, then you could have written this as minus T nR dV by V, right? And you would be able to get minus T nR ln V2 by V1, initial volume to final volume, right? You could do the same thing for a van der Waals equation also. The algebra won't be simple, right? The calculus won't be simple. You will have to work with everything. So equations of state are very useful for processes being carried out reversibly. And equations of state can be calculated. People can calculate equation of state by doing simulations. People can calculate equations of state by literally carrying out an experiment, right? You take a block of a sample and you measure what is the volume of the sample at a given pressure at a temperature, right? And you come up with these surfaces, the pressure, volume, temperature surfaces, and you fit this surface. That is an equation of state. So equation of state is something that is routinely measured in different experiments, and it's super useful in order to calculate these things. Okay, so thanks, Dosia. Now we go to Sanjana. Very good. F is equal to C minus P plus 2. And the 2 really comes from this pressure and temperature, right? One of you wrote in your homework. That's where it comes from. A Gibbs phase rule is, why is it important?
That's because, so it basically defines the number of phases that can exist for a number of components at a particular point in the phase diagram, and so we can just avoid quadruple points or.
Yeah, so for example, it tells us that for pure water, you can at best have a triple point. You cannot have a quadruple point, right? And as we saw later, when you have multiple components, or even in a single component system, it might not exist as a solid, right? Water exists as solid, liquid, gas. And if you want to capture where is it going to be solid, where is it going to be liquid, where is it going to be gas, we map it in a phase diagram as a function of two intensive coordinates. That's something to keep in mind. Phase diagrams always have intensive coordinates. It's that you could do it for extensive, it just doesn't make much sense. And this becomes very important. So, like if you are going to search for water on Saturn, you're not going to be looking for liquid water, right? You would probably be looking for some form of ice, right? Which form of ice? What will its spectra look like? you can know from the pressure temperature phase diagram. And it doesn't matter that the phase diagrams, the amazing thing is the phase diagram is going to be the same, whether it's for water on Earth or water on Saturn or water in, what's the furthest object any one of you know from the Earth?
In the solar system.
No, let's go far, like really far.
Andromeda Galaxy.
Andromeda Galaxy, but that's kind of close to, right? Like, let's go further.
The Crab Nebula.
Huh?
The Crab Nebula.
It's just making it up. It's a real nebula? The
Yeah.
Crab Nebula?
It's like the most famous nebula.
Oh, really? Okay, good. Good. So let's go to Crab Nebula. There also we can expect the same equation of state will, the same phase diagram will hold true. Can we be really sure about that? I don't know. I really don't know, right? I mean, we haven't gone there, but so far it seems that if these thermodynamics really holds true, irrespective of where you are in the universe, right? If you go to the center of a black hole, then you're out of equilibrium, right? That's not going. So as long as you're at equilibrium, phase diagrams apply only to equilibrium, right? And so the problem with the phase diagram is it tells you what phase will form if you waited very, very long, right? And how do you know how long? No one knows, right? And that's the problem of thermodynamics. All of this, what we have done, really applies to systems with number of atoms tends to infinity, volume tends to infinity, and density a finite number. Is that ever true? No, we have a finite number of atoms. We know that, right? Does anyone know the number of molecules in the universe? It's less than 10 to the power 60. And the reason I remember this number is because I always say that the number of possible drug-like molecules one can synthesize is around 10 to the power 60, which is more than the number of atoms in the universe. So I know it's lower than Avogadro number of Avogadro. It's more than Avogadro number of Avogadro number, which kind of makes sense, right? Avogadro of Avogadro. So even that is not infinite. It's a finite number. If you take its log, it's 23. On log scale, it looks like a small number, right? 23. Anyway, so Gibbs phase rule is useful because that's the first step you have in drawing a phase diagram. Without Gibbs phase rule, you will go completely blind. Then there is much more to drawing a phase diagram, right? You have from theory or from experiments, because a phase diagram at constant pressure and temperature is really understanding the Gibbs free energy and how different Gibbs free energies compare to each other. And as you saw, we had conditions where we had two Gibbs free energies existing like this. Let's say it's the free energy of mixing, and we had non-trivial behavior in the middle over here, right? It could split into a mixture of these two phases, right? But the Gibbs phase rule is still your guiding light. You have to use that. Okay, Shah, you have been very silent last few weeks. What happened? Everything okay?
Yes.
Yeah. Okay. So tell me your favorite equation.
The second law of thermodynamics for phases.
Which is?
Chemical potential of phase, let's say, 1 is equal to the chemical potential of the same species, but
In a different phase.
Yeah.
And as you saw in the homework, this equilibrium, this sets up the direction in which matter moves, right? If chemical potential is the same, the matter won't move. You can just have, and that's what happens in this thing, right? You have two phases, the blue and the red coexisting. And you would think, well, blue has a lot of A and red has a lot of B. Red has more A than blue, something like that, right? Why isn't the A moving? It's not moving because the chemical potential is the same, right? And why is chemical potential here the slope? That goes to partial G by partial N relation. That's where it comes from, right? Okay, good. Jock, did I ask? No, even if I did, you're undergrad, you get special status.
I already gave you an equation.
Tell me another one.
You told me specifically that if I raised my hand and gave the explanation for the whole.
You could argue or just tell me an equation.
I can give you like a concept. We've been like.
Okay, tell me a concept. But that would be, it would make me so happy to give me an equation.
It would make me so not happy.
No, I think you will find this, it will be delayed gratification.
It's a later, yeah, sure, okay. I don't know, like first off, we go like D is delta Q.
Yeah, there we go. dE is equal to delta Q plus delta W. This is what I was fishing for. Okay. Now tell me here, what is E? E is the change in internal energy of the system, right? Of E of the system. And Q is heat given to the system. And work done on the system. And it's great that you bring this up a joke because you pointed out my Twitter spat. No, it's not a spat, it's a friendly discussion with Zara from UPenn. She was like, just do first law and it's all there. No, first law doesn't have everything because first law tells you that this water falling on my hand like this, dE is equal to dQ plus W, and the water suddenly appearing back and going into the glass, both follow dE is equal to delta Q plus delta W, right? First law does not tell you that only one of them is actually going to happen. Statistical mechanics does not tell you that only one of them is going to happen. It's the second law of thermodynamics that tells you that one of them is going to happen, right? So, but yeah, so remember this equation, and always, again here, remember, dE is a state function. It does not matter how the process is carried out, which can often appear magical because you might be carrying a process in one way. As long as you know what are the two endpoints, you can calculate dE in a completely different manner. It just doesn't matter. dQ, delta Q is path dependent, delta W is path dependent, right? And delta W can be more general than just PDV work. Normally we stick with PDV work. So this equation becomes dE is equal to delta Q minus, and here super crucial, what Dosia said, it's P external dV. Don't be tempted to just replace it with ideal gas law unless you have been told that it's a reversible process and it's an ideal system, right? So maybe there is no other way to proceed. In that case, you should make that assumption. And I'm not just talking about this exam. I'm talking in general. When you're working in any system, you have to think carefully what you want to do there. Okay, and you wanted to add another concept? Huh?
Okay. I like the idea that, I mean, most of it just boils down to there is something that is either maximized or minimized.
Yeah.
It's like entropy or
Absolutely, absolutely.
and that's like with that interpretation.
Yeah, that's what I meant. Like, and that comes down to time. Time is always going up. It's like universe is in a hurry to increase the time. That's all. And it's getting metaphysical. But the more I teach thermo, the more I feel the universe is like, let's go there. Let's get there. Are we there yet? Are we there yet? And so universe is always moving in one direction, right? So there is something that is always increasing. And that is really the heart of why should there exist an S of NVE, right? That is the heart of it, right? That in a closed system, this is always going up. In an adiabatic process, it cannot, unless you are reversible. If you're reversible, it's zero, right? But if you're for spontaneous change, it should keep going up, right? Okay, Maria Delia.
Well, here they state Paul's second postulate, so the derivative with respect to E will be always greater than
Partial S by partial E at constant NV is always positive.
and the derivative with respect to B.
Okay, question for Maria Delia. How about this one?
That one, I remember that you said that we cannot.
Yeah, we cannot say anything, right? And this is important because S is extensive. If something is extensive, you are tempted to think, right, that if you increase the number, entropy should also go up. The reason that does not lead to this equation is because of constant volume and energy, right? Extensive does not imply this because if you double the thing, volume and energy are also going to double, right? So we cannot say anything about it. We can only say things about these two. The first one has implications. What are the implications of the first equation? You can answer Maria Delia, or you can just pass the bait to Elizabeth. Come on, I wanted you to answer. Come on, tell me. Help me. Yeah, why was this important, this equation?
I remember that was.
Let me give you a hint. I cannot say tomorrow the temperature is going to be minus 40 Kelvin. That's your hint. Temperature. Yeah, there you go. So what is temperature? Temperature is partial S by partial E at constant NV, right? That is the definition of thermodynamic temperature. And this tells you the temperature must be positive in Kelvin scale. Next semester in StatMech, you will see temperature can be negative, and negative temperature is hotter than absolute zero. So it's very crazy, but that happens because you are in systems where N is not infinite. It's a finite size system. So this sets that temperature is going to be positive. Okay, Elizabeth, you want to take a shot at what is the other implication of this equation? What else did it allow us to do? Yeah? That comes from the second equation. Yeah, but the fact that S and E are monotonic increasing, that led us to doing something. Do you recall that one?
So this,
Almost there, almost there. So we wrote down, so second law only, when Callan's postulate only says that there exists S of NVE, it's only due to this monotonicity property that we can write down there exists an E of SNV, right? We would not have been able to do this back and forth. If you had a function that was going like this, right? Then you cannot say that at this point, what is the value of the x-axis? It could be one of either three, right? The fact that it is monotonic. Monotonic means that S of E can look like this, or it can look like this, or it can look like this. And now comes the concavity. Concavity says that it's going to look like this. Or did I get it wrong? What is the concavity equation? No, you're done, unless you want to do it. I'm being nice. She's nodding her head. Okay, Elizabeth, we stay with Elizabeth because Maria wants us to stay with Elizabeth. No, she wanted us to go away. She can do it. Okay, tell me. I know she can do it, of course. I believe in all of you. So tell me, Elizabeth, the concavity equation says partial double derivative of S with respect to is positive or negative? Negative. Which means the derivative is becoming smaller and smaller and smaller. I always trip on these things, but the way to remember it is that things that are maximized have double derivative negative, and things that are minimized have double derivative positive. You know, that's one way of thinking about it, but it's easy to forget it. So only this one is correct. These two cannot be correct. Okay.
It can be less than or equal to 0.
Sure. Sure. At critical point. Let's not go to critical point. You're bad news. People who work with attosecond stuff are bad news. What is attosecond? I cannot understand. I really cannot, because uncertainty relation says that delta E multiplied by delta T is Planck constant, right? So attosecond means the uncertainty in the energy must be crazy high. Okay, come to my office and explain to me. Wendell has not been able to, so. I mean, no, but he was in a rush. You will have more time, I hope. Okay, so this is our concavity relation, and this then this led us to showing that entropy is maximized as you get to equilibrium, right? And I have pointed out a few times to you on Slack. I will again point out, go and prove that in the energy representation, this means the energy is minimized, okay? Which makes common sense. We always try to think, right, that, oh, we should be in a low energy configuration. But we use that term casually. We should be in a low energy configuration if the control variables are entropy, number, and volume, right? And that sounds very strange to me. How would you design an experiment where the entropy is the control variable? That's very strange, right? I don't know how to design such an experiment. So even though we think that a system likes to go to a zero temperature, a lower potential energy, that concept is actually, and this is again where I often rant about, sorry, Stephen, inorganic chemists and people using DFT, because they use these things very casually, right? So at zero temperature, sure, nothing matters, right? And you can go to a potential energy minimum, but otherwise you always need to think about free energy, and or whatever potential depends on your control variables, right? So it's always a game of control variables. Okay, yeah.
Because energy is a state function, can I like re-express it in the variables that I want? I'm still going from
It won't be a fundamental equation though. You will be losing some information. That's the problem. That's the problem. And I also want to point out that Callan has a chapter where he has surfaces, he has printouts, he has drawn like 3D surfaces on the page where he tries to give you intuition into entropy concavity, maxima, and energy minimization. He draws planes through the surface and gives you intuition. It's worth going in. Okay, Zachan. Yes, but do you remember any of them? That's clever. Tell me, if you can tell me one Maxwell relation. So that sounds like Jock speaking French. I don't know whether it is true or not. Okay, that's why I said, because no, so Jeff Clouder told me he remembers over dinner 2 nights ago that he remembers all the Maxwell equations. And I was like, wow, good for you. Because I will never remember them. What I want you to tell me is to how to derive it.
Yeah, I just did that.
You did it in your head, I know. So do it on the page.
From the
So dg is equal to, and then how do we get the Maxwell from this one?
So you got pressure. Constant temperature.
And number. So I think this is correct, but I do recommend writing down the Maxwell relations. It's like those commercials where they say, don't do it at home. So even though he did it right here, I would say, don't do it in exam, okay? It's easy to derive, and this is the concept that you should remember, right? So similarly, we can get 4 other Maxwell relations by writing down the 4 different fundamental equations, right? We did G, we can do H, we can do A, we can do, which one else? Huh? How about S? Why can't we have a Maxwell relation from S? We didn't do that, right? There are only 4. When you do it, you will realize that one of them is repeated. You will get the same Maxwell relation. You just go and try it. You won't get a new one. It will look different, but it's not. Okay, thanks. You were extra brave, so I won't ask you a concept. Okay, Lynn? In entropy relation? Okay, but can you tell me the equation though? I will let you look it up because I will write down. You have it in your notes or you probably remember it. Tell me again, df is equal to 1 by t multiplied by de. Yeah. Okay. dv dn minus mu over t dn. Okay. So I wouldn't call this the Gibbs-Duhem equation. I would call this the fundamental equation for entropy. Yeah, it has some other name. Even if that's okay. Maybe if you don't remember the name, that's okay. The names of the equations that you need to remember most importantly are the fundamental equations for all. But that's correct. You want to tell me a concept? Then? Okay, let me give you a hint because we are also we have covered most of the things. Which one is higher, reversible work or irreversible work? Why? When you have an engine which is trying to do some work, and if the engine is taking some heat and changing it into work, the engine can be working reversibly or the engine can be working irreversibly. In which case will you get more work out of the engine? It's reversible, right? It's an irreversible means you are dissipating more heat out to the environment, right? And the reason I bring this up is because this led to the whole thing about Carnot cycle, like that, right? We looked at Carnot cycle having the highest efficiency, and we showed that thing that all reversible cycles working between T cold and T hot must have the same efficiency. And that is Carnot's efficiency, right? And that's a very important relation that tells you, for example, if you are interested in artificial photosynthesis, there is a limit. And that limit might be very, you can calculate that limit. You're not going to beat that limit. Anything, battery, not battery, but any sort of fuel cell, there's a limit. It tells you the limit that you're going to achieve in that case. Okay, thanks. Lydia? What?
dP by dt is equal to delta S over delta.
Where did this come from?
That's Avalon.
Oh, yeah. So it's not dp. Should I write partial or should I write d? It's d. Okay, so this is problem in transcription on my side. So what you're saying is dp by dt is equal to delta S by delta V. Okay, now it looks familiar. Can you tell me how to derive it? The key idea?
No,
Why not?
it's from phase diagrams.
No, but you can see the sign here, right? It's really saying that dp delta V minus delta S minus dt delta S is equal to 0, right? So it's looking at something where the natural variables are p and t and n. So it came from looking at the boundary on a phase diagram and saying that as you move from point A to point B, the change in Gibbs free energy should be equal to the same, right? So we use the fundamental equation of dg of g to write this down. And this was Clapeyron equation, right? This one, anyone remembers the Clausius-Clapeyron equation? Or the key idea in Clausius-Clapeyron? Ideal gas, right? So we said that delta V is equal to V gas, approximately V gas, right? And we use here V gas is equal to nRT by P, right? I even don't remember Clausius-Clapeyron because it's inexact. I can always derive it. It will take me 30 seconds and it's okay. But this one is exact. Clapeyron equation is exact. And I will write here something because I don't remember this. Clausius-Clapeyron is approximate. Okay. Good. Any other concepts you would like to add, Lydia? No? Okay.
Phase diagram.
Phase diagram is a good concept. I agree. Rohan?
I guess the entropy of mixing.
Oh, yeah.
with
Oh, yeah. Delta mixing S for,
I guess so. Two components.
yeah, two component. Tell me.
So X and then X.
X1, L1, X1 plus X2, Ln X2.
I guess this could be generalized.
This could be generalized, but what is over here?
R.
Minus NR or plus NR? Why? Because entropy of mixing is always positive or negative. Should it be minus or plus? So when you mix something, let's think about an ideal equation. Why should the entropy increase? Because the contribution to the Gibbs free energy should be negative, right? But as we know, entropy should be maximized. Gibbs free energy so entropy should be positive. Delta S should be positive. And X1 and X2 are mole fractions. Log of X1 and X2 are negative. So you have to multiply it with a negative number. And this is related to Shannon entropy. In your StatMech, people call it Gibbs entropy. You will see that. If you read books on StatMech by McQuarrie, there is a whole way of doing StatMech where you start with the Gibbs entropy and derive all the different ensembles. We don't do that at Maryland. We look down upon that way. Again, it could be one of the Twitter discussions. There you add Lagrange multipliers and things like that, and there's a whole lot of issues there. But yeah, so you will see equations like this in your StatMech also. And this equation was very nice because we know that we use L'Hospital's rule and show that ln of x1 is minus infinity, like that thing when you go to either. We looked at the slope and the value and we saw it goes to 0, but with a slope of minus infinity, right? So when we plotted this thing, it looked like this, right? Depends on what I'm plotting. I might be plotting. So here I am plotting minus t delta mixing S, right? So I've taken this thing and multiplied with minus t. So which means that things always like to mix. It's very, very hard to create a pure system. You're fighting against entropy, especially as you go to higher temperatures, right? And this equation is also important because even though there is a delta H part, right, which we don't know how to deal with, we had a regular solution model and everything. But as your temperature becomes higher and higher and higher, this is the thing that will dominate, right? So as you go to higher temperature, this does become a guiding force. Okay, Matt?
For an ideal gas, G is equal to G naught plus nRT times ln of
That is the same as, okay, I will allow this. So this is really the same as mu is equal to mu naught plus nRT ln, right?
Yeah, if you divide by it.
If you divide, okay, I will give you that.
Totally
Now,
different.
now you better tell me a good concept. Don't do a phase diagram on me.
You didn't even know my equation.
I know, I'm not taking exam on this, FYI. I'm gonna be sitting here and tweet fighting someone.
I was gonna go back to the conversation we were having on Slack, but I was getting intuition about the slope of the chemical potential.
Yeah, that is the let's talk about the common tangent construction. Like that's a concept you should remember. It's beautiful, right? When we have, that's more than an equation. That's really a concept, right? When you have a free energy of mixing that looks like this, and you have another free energy of mixing that looks like this. If you just look at this naively, you would think that for all of the concentrations to the left of the solid black line, this should be the stable phase. And all of the concentrations to the right of the solid black line, this should be the stable phase, right? But that's not true. You find that if you draw a common tangent here between these two, and there is only one such common tangent, and again, Anjali and Ben are going to kill me for extending the line towards here, but you see my point why I do that, right? In between these two, the system will drop down into a combination of two phases, phase coming from here and phase coming from here, right? And the concentration of these two phases will be the same, irrespective of where you're dropping down, right? And this was a very important concept because when we look at the phase diagram of like boiling of anything, the vapor that comes out, if you're boiling a mixture of two things, the vapor that comes out will have the same concentration of the thing in the liquid. This is not obvious at all, right? You would think like, well, maybe the thing is going away, the concentration of vapor should change. No, that's how fractional distillation works. You know, the vapor is always at the same concentration. And you can calculate this. Later we talked about Leeuwenhoek, right? Which allowed us to calculate from this. Okay, thanks, Matt.
Point concentration, like density, right?
Yeah. So, okay.
And it's by LP at constant pressure CP.
Oh, yeah. How can we forget that? So I'm going to take a step back, and I'm so glad you brought this up. So when we wrote down dE is equal to delta Q plus delta W, we say that this is equal to, for only pressure volume work, this is delta Q minus P external dV, right? So, okay, that doesn't give us much practicality of how to do it, right? Because if we know what is the pressure that is being carried out, we can do it. If we know it's a reversible process, then we can replace P external with P system. But it doesn't tell us much about delta Q, right? So that's where we had to think, what can we do with delta Q? And that led us to two very interesting relations. We said that delta Q is equal to du for a process happening at constant volume. Notice we did not say that it's a reversible or an irreversible process. And that's super beautiful, right? Because it just doesn't matter. If it's a constant volume process, this path function can be calculated from the difference of a state function, which is so awesome, right? And what Sarat said is delta Q is equal to D of H. That's how we introduced enthalpy, right? For a process happening at constant pressure. And this then led us to conclude that CV, which is delta Q by delta T at constant volume, is actually partial U by partial T at constant volume, or heat capacity is a state function, right? Because it's not obvious to me, why should heat capacity be a state function, right? You're heating something and maybe it depends on the path, right? But it doesn't. If it's happening at constant volume, then it doesn't. If it's happening at constant pressure, then once again, Cp is equal to delta Q by delta 2 at constant pressure is equal to partial H by partial T at constant pressure, and it's a state function. We can calculate it. So we can just say, this is the Cp of this material. We don't have to say, how are you heating this material? That's non-trivial. That's really non-trivial, because where does heat capacity come from? You will see in the next semester. The heat capacity really comes from molecules moving around, right? Or electrons moving around. So, and this gets really complicated, and there are some unanswered questions here. So when you pump heat into a system, what does the heat do? It goes and makes the atoms vibrate faster. It goes and makes the electrons wiggle faster, right? Now in quantum mechanics, the first approximation we make is Born-Oppenheimer approximation, right? So you can assume that maybe the electrons And electrons are much faster than the atoms, right? But in reality, as the electrons move, they actually affect the atoms also. But this is known as electron-phonon coupling. So the heat capacity becomes really, really complicated. And you would think, well, all of this so complicated, it should definitely depend on the path, on how I'm giving the heat. But no, it doesn't matter if it's a constant volume process. The microscopics disappear. That's the beauty of thermodynamics, right? We all feel tempted to think about atoms and everything. But there is a problem with atoms. What is the problem with atoms? There are too many of them, right? There are too many of them. When I go to some experimental conference and show this is my protein kinase and here I've done my simulation, every once in a while there will be one experimentalist who gets very angry. Like, oh, there is no cell over here. There is no this, there is no that, right? Thermodynamics is powerful because all these descriptions don't need atoms, and yet they hold true, right? It does not matter whether the thing is made up of a polymer, of a fancy quantum material, or something in, what was the galaxy you made up? Crab
Not
Nebula.
make up anything.
You made it
So
up.
not a galaxy. It's also something that you've definitely seen before if you've ever seen it.
I don't know.
Didn't you say that like CP was higher than CP?
Oh yeah, very good. Why is CP higher than CV?
Some of that heat is lost. Like,
And this was the question that I had really asked Chris. So no one really got it right. You all came close. We started thinking about phase boundary, which is correct. It's connected. So the question I asked Chris is, when we explained why is CP more than CV, the idea was that if something is heating and it's a constant volume, whatever heat you give to the system goes into making the atom vibrate more, right? But if it's a constant pressure, some of it will also go against piston. But that's if the thing expands. If it's a negative thermal expansion material, then as you give heat into the system, it will actually contract. That's water between 0 to 4. And there are a whole class of materials known as invar materials where this happens. So there it would have appeared as if CP minus CV should be negative, right? But the arguments there, as you saw, using Maxwell relations show that no, that is not the case. Yeah, so CP minus CV is equal to NR for an ideal gas. For a non-ideal gas, it is still more than 0, and the expression can be derived in 2 or 3 different ways. Okay.
We also know the thermal.
Yeah, so in this relation, that comes up as an alpha square. That's the beauty of it, right? If it was negative alpha, then we would have trouble. But if you go and look at that equation, it is square of alpha. So even if it is negative thermal expansion, CP minus CV will have the same effect. That's just crazy. Okay.
So what is the argument that we could actually use CP and CV interchangeably? And
Oh, you asked me this before also. Oh, yeah, Shah is freaking out. There is no argument. They are different from each other. You should be careful.
yeah, but there was a reason that it is allowed to use. For
No, it's not. Who told you?
No, remember
It's
I-
sloppy. It's sloppy if you're using them. You should be careful which one you're using. People are sloppy when they do that. You go and smack them. Which C are you talking about? You cannot use them interchangeably. They tend to behave with temperature in a similar manner because CP minus CV differ from some things, right? So no, I would not use them interchangeably. Why do you want to use them interchangeably?
No, it's not.
It's sloppy science when people do that.
No, I remember that I told you.
I
where
was
they-
sloppy.
No, I said like where this is being done, and you said, oh, this is the reason.
You have to slack me. This has forgotten.
I mean,
But
there was a time when like we were looking at something that wasn't at like constant volume or wasn't at constant pressure, and we still used the relation, like we still like plugged it in. Like I think we were doing something that wasn't.
then
at
it must be
constant-
because we were talking about endpoints. If it's a state, we are talking about the difference of a state function, then we can. You have to remind me what it is. I'm forgetting. We have done 24 classes, right?
No, yeah, I'm just saying, like, I think that might be like what.
Yeah. But remember, CP and CV are different, and the different depends on these alpha square, like square of thermal expansion coefficient, and it could be non-trivial. However, and I'm going to draw it here, you will see in StatMech that both CP and CV, as a function of temperature, at very high temperature, they go to 3R, and at low, this is temperature, they both go like this. This is the behavior. Okay, and this is where you will see that Einstein was lazy, he got it wrong. Einstein got the relation, this is e to the power minus kt, and Debye got the relation, it is e to the power cube, something like that. And Chandler gives this in his book, which you will be studying next semester as a homework problem. It's a terrible idea. I take 2 classes to do that. So if Gary gives you as a homework problem, you tell him, like, no, that's a two class problem. So yeah, CP and CV will differ. And yeah, go ahead.
So enthalpy is a state function.
Entropy is a state
No,
function,
no.
sure.
Enthalpy H.
Enthalpy is a state function, correct? Yes,
So that's why, because if it was the endpoint, then we could.
sure, exactly. That's the point. Okay, Rashid, I'll come back. You want to add an equation? Oh, good. Okay, I will
So
go to
can
you.
you go back a slide? I don't know, this hasn't like come up at all pretty much the entire semester.
Maybe for a reason.
E versus U. Are they,
They are the same.
they're the same thing,
Yeah.
so you put them both on the same slide because you're fun?
No, because when I taught 481, I used U, and this time I used E, and I was copying an exam problem from that. Didn't you notice? You were the only one who noticed in the second midterm. Then I said, explain unity concepts from Chem 481. Because I gave a similar exam in Chem 481 also. That's why. I must say the PowerPoints in the undergrad TCM are way funnier.
I don't remember.
You didn't take mine.
That's
My
true.
PowerPoints have like Pokora wearing lab goggles and things like that. in undergrad. I'm going to declare the prize for the funniest PowerPoint in this. Huh? He's become a bastard. Last night he beat my wife. I'm serious.
If
I'm
you don't-
serious.
If you don't want it. I've got-
No, I will keep it. We have Megan's friend is visiting with a 2-month-old baby, and Pokora like got jealous or something. So he was like, why isn't everyone giving me attention? He just went and beat my wife. So we have boarded him for 3 nights. So he's away because it was getting like stressful. He has an all dogs club. Okay, Rashik.
E equal to TS minus PV plus Q.
E is equal to TS plus mu n. So yeah, this is an equation which is kind of non-trivial, right? Try to, yeah, I'm so glad you brought this up. Please derive it for practice. Where did it come from? It's a non-trivial derivation. It uses that Euler homogeneous equation and things like that. And this was very useful. We have used it for things like the grand potential and things like that, right? So remember this equation and the concept.
Is like we use the postulate, like the extensively postulate to get a functional form of.
Good. Okay, come here. Oh, absolutely. Thermal efficiency is work that you get out of the system divided by the heat that you get into the system, right? Which makes sense. Like I ate this much food and I ran this fast or something like that. Okay, and then the concept. Yeah, and reversible efficiency is always more than equal to eta irreversible, right? And we saw between the same 2 temperatures is Carnot efficiency. Ben, did I go to you already? Oh, good. So we're done. See you all for the exam. What?
I want to add one more equation.
Oh,
Again,
wow.
this
Okay.
Gibbs equation.
Uh-huh.
on this del T of capital G by T equals to minus of capital H by T square.
Gibbs-Helmholtz. Yeah. So you are saying D of delta G by D of T, something like this, right? Is equal to
Equals to minus of del capital.
delta H by T squared. Yeah, we did this one. Gibbs-Helmholtz is useful because if you measure the enthalpy change in a chemical reaction, which you can do using CP, you can go and talk about free energy change, right? So you can then talk about how would this reaction look like in constant pressure conditions. Good. You have a question?
Did we say the integrated first and second law or no?
Oh, yeah, that's the most important equation. What's the integrated first and second law?
I think it's DE equals TDS minus TDB plus UDN.
So we said and did not say it because this is the fundamental equation for E, right? So the fundamental equation for E is the most important equation in second law in 684, right? If you start from here, you will get everything. Okay, any final questions? Yeah.
For that, Gibbs Helmholtz equation, does that assume ideal gas or is it valid?
No, I don't think it assumed ideal gas, did it?
I haven't asked.
No, I have forgotten.
They are also like capital G by T as well. Like del of
Yeah.
capital G by
Let me check. It did not assume ideal gas, and it was partial G. Yeah. It was very powerful. Otherwise, it would not be that powerful. d of delta g by t by partial t at constant t is minus delta h by t square. And this was not ideal.
Okay, the other question was like, I always thought that the Carnot engine was like the most efficient engine, but then I remember like on our second exam.
The Otto cycle. The Otto one.
Yeah, sorry, I said motor. But then you were saying that like the Carnot theorem is actually that like you were supposed to show that all reversible engines.
Yeah, the Carnot theorem here is specific. It is between a heat sink and a heat source. The other engines, if you really want to compare, you have to construct them so that they are between the heat sink and the heat source. Between the same heat sink and the same heat source, Carnot is the most efficient. That is always true, which we proved.
So for the auto cycle, you wanted us to show that they would have the same between the same sources?
Yeah, that's why it was a bonus problem. It was not the full point. You could construct, and I posted that solution, but you can see, you can construct, and that's why it was non-trivial. You could construct it, and then you could show that it is the same. It was non-trivial. Oh, by the way, there will be a bonus problem on the final exam. Many of you don't even touch the bonus problem. Please write something. I give partial credit. He can attest to it, right? He got 0.05 points. Yeah, what was your answer? I showed it to Chris.
It was,
Yeah, he said, oh, Jock, I remember, funny guy.
funny guy, like,
Yeah.
he did write me a letter of recommendation. I'd like to notice that, like, you gave me that 0.05 extra points. My grade was still 105 out of 100. not
Yeah,
105 points.
Sure, but I will remember it if you're hanging between B minus and B plus. B minus and B, I will take that into account. Okay, let's stop and not get more degenerate. See you all Wednesday morning. And ask me questions on Slack. This weekend, I will try to respond a bit